Welcome to fields. A force field is anywhere where you can experience a non-contact force, and we're going to be looking at three types. We're going to be looking at gravitational fields, magnetic fields, and electric fields. Gravitational fields exist around objects with mass. They can even be objects with very small mass. These two objects will interact and exert a non-contact force on each other that is equal and opposite. Magnetic fields exist around magnetized objects and exert force on other objects, such as iron, nickel, and cobalt. Magnetic fields also exert forces on moving electric charges, both positive and negative. If they have velocity and they're moving in the vicinity of a magnetic field, then a force will be exerted upon them. Electric fields are exerted around positive and negatively charged objects. We can represent fields using vectors. So here are the force fields from mass. For a magnetic field, notice that these lines do not cross. And an electric field from positive to negative. The direction of these field lines is given by the direction of the force that would be exerted on a test object. So for example, if I was to put a test mass inside this gravitational field, it would experience a force attracting it to our larger mass. And these force field lines exist throughout all of this space. The same for a magnetic field. The directions show the force that would be exerted upon a test north pole. And here in the electric field, if I was to place a positive test charge, it would be attracted towards the negative plate. In these first three examples, we have different shapes of fields. We have radial fields and we have a uniform field, but we can also get the other type. So if you zoom in very close to the surface of the Earth, then the gravitational field appears to be uniform. If you zoom in to a north and south pole placed close together, then you also can get a uniform magnetic field between the poles. In the top example, we can see a uniform electric field, but if we analyse a positive charge on its own, we can see that the force lines come out of this. We have a radial field. If we analyse a negative charge on its own, those field lines are coming in. Together, if they are both present, a positive charge and a negative charge, those fields would interact. You need to know some important differences between gravitational fields and electric fields. Both of these can have uniform fields, and they can both also have radial fields. The gravitational field is attractive only. Masses are attracted to each other, they cannot be repelled. Whereas electric fields, you can get forces of attraction and forces of repulsion. They attract and they repel. It is useful to know that gravitational fields are relatively weak when compared with electric fields, and this is because the constant of proportionality for each field, big G, and 1/4 pi epsilon subscript 0, this is a very small number, times 10 to the minus 11, and this number is very large, times 10 to the power of 9. And that causes gravitational fields to be extremely weak compared with electric fields. You are already familiar with the concept of potential. For example, potential difference. 1 volt is 1 joule per coulomb, or work divided by charge. You are also familiar with gravitational potential energy, or mass times gravity times height. If we rearrange this formula so it resembles this one here, energy per unit of what is affected by that field, then we get the amount of energy per unit mass, or GH. And this give us the amount of energy that is required to move 1 unit of a body that is affected by that field. So for gravitational potential energy, you know that you need to put energy in to raise an object to a height above the Earth's surface. And gravitational potential, or V, is the energy per unit mass. And for an electric charge, that would be the energy per unit charge required. As well as potential, we have equipotential lines. So notice that these movements, these change in height and change in distance, are along the field lines. If we redraw the field lines, then we can also sketch on lines of equipotential. So in the same way that if you are walking up a hill, you have to expend energy to get to the top, you could stop at one point on the hill and walk around it at the same height. Here is an equipotential line going around this mass, and here is an equipotential line going around this charge. To raise a mass up to this level here requires a certain amount of energy. It takes the same amount of energy to raise it from this position up to there. But if you then move that object along the equipotential line, you're expending 0 energy to do so. Same for a charge. If you move a charge up to this equipotential line and then move along that line, it took energy to get up there, but then expended no energy moving it along that line. You also get equipotential lines in uniform fields as well as radial fields. So here is a uniform gravitational field, and here is a uniform electric field. The equipotential lines here are like this. Notice that in both cases, the equipotential lines are at 90 degrees to the force field lines in all cases. One major difference between radial fields and uniform fields is the inverse square law. Where you have an object with a radial field, this might be a mass with a gravitational field, or it might be an electric charge with an electric field. The field lines get progressively further apart as you go further away from the object. And if you imagine that this diagram was in 3 dimensions, then these field lines will be coming out in 3 dimensions. And the equipotential lines would be describing the surface of a sphere. The surface area of a sphere is given by 4 pi r squared, r being the radius between the centre and the surface. So if the surface area is increasing proportional to the square of the radius, then the strength of the field is decreasing in proportion to this. The strength of the field is being spread across a greater and greater area. So if this was the study of a light source and the light intensity as we get further away, then the light intensity is going to be decreasing the greater the area. And therefore, it's going to be connected to the square of the radius, the inverse of the square of the radius, the inverse square law. With fields, the strength of the field, or the force that the field is able to exert, is also proportional to the inverse of the square of the radius. For example, with gravitational fields, the equation is we have our constant of proportionality, our 2 masses, all over r squared. For an electric field, this is slightly more complex. Our constant of proportionality is 1 over 4 pi epsilon subscript 0, multiplied by our 2 charges, all over the square of the radius. Both radial gravitational fields and radial electric fields obey the inverse square law.